Hi everyone and welcome to the third tutorial of this module. Today's topic and example are based on a real-life case study, and personally I find it very interesting from a problem-solving point of view. So today's tutorial is about the design of water distribution system and more specifically about the rehabilitation plan for the New York tunnels problem. The objective is to find the least cost rehabilitation solution that meets the future demands whilst satisfying the minimum total head constraints, which we will see in table 1 in a bit. So I want to highlight here the key phrases of this sentence. It is least cost, meet future demands, and minimum total head constraints. As I mentioned in previous sessions, IPANET assumes that all demands are satisfied. So it solves the system of hydraulic equations and calculates pressures based on that. So actually, we have to find the least cost solution that satisfies the minimum total head constraints. That means we have a two objective problem. So let's jump into this graph here. So this is our network. This is the current state of the New York tunnels water distribution system, let's say. Now, due to various reasons, this system is not capable to satisfy the desired criteria, like the minimum pressure at demand nodes. So the suggested solution is to add parallel pipes at specific points in the network. This could be in any point between two nodes, so actually between these pipes. For each pipe there are 16 possible different actions, so do nothing is the first option, and then the rest of the 15 options is to add a pipe. This pipe could have any of the above 15 diameters, which are these right here, and these are in millimeters. Now the cost of its pipe is calculated from this equation, where D is the diameter in millimeters and L is the pipe length. In table 1, down here we can see the node data, which has the elevation, the demand, and the minimum required total head for each node. And in the second table we have the pipe data with these known parameters like start end node length, diameter, and pipe roughness. So jumping into IPANET, here we can see the network model along with the duplicated pipes at all positions, as you can see here. So note though that all these extra pipes have a diameter of 1 millimeter, which is basically negligible, and it's not going to have an impact in the network's hydraulics. We can see this here. So if we now run the simulation, let's see some more information. You can see the IDs, and you can actually see that this node values. Yep, so okay. So now we can see on map the pressure for each node. I'm going to change the colors here because it's a bit too bright, the yellow. Yeah, okay, let's do it red. Okay, and maybe let's see it in larger font. Yeah, okay. So now these are the pressure values at each node while we have done nothing. We have not added any extra pipe, etc. So let's compare these pressures with the minimum required pressures. So I'm going to jump back into the handout and going to stop here. So I'm going to minimize this window now so that we can see all the values. So we see that on top of a network, for example for node 2, the required total head is 89.7, whilst the simulation says we have a pressure of 89.31. If we move along for node 3, it's about the same, like more or less 1 meter of difference. Same with the rest of the nodes. If you see, going from 4, 5, 6, 7, it's very close to the needed values, to the minimum required values for pressure. So it's the same for all nodes up until this point. I think we have for node 9 and 10, then 11, 12, 13, 14. It's all very close to the desired values. Now if we go though to node 17, we see it's 80 and the required one is 83, and if we go to nodes 16, we see the required one is 79 and we have a 64. If we go to node 17, yeah, I said this earlier, so it's 18, which is 79.5 the required one, and we have just 47. So this is what the biggest difference so far, along with node 16 and also node 19, which should have pressure over 77.6 meters. Same with node 20. So I would say that the most critical nodes are these ones that have a difference of pressure more than a couple of meters. So the deficiency at node 19 I think is the highest. We have a simulated value of almost 30 meters, and the desired one is 77, which is quite a big difference. We can manually solve the problem of the second task, which is to try to minimize the cost while maintaining the required head pressure across the network. So we're going to add pipes at some points and see if we're improving the network's hydraulics or not. So we have to update pipe diameters and then check if the pressure head across the network is fulfilled. Now we're going to use some tool in order to calculate automatically the cost of its solution, and I'm going to show you this right now. So this is the spreadsheet I have provided you with. For now, for this like manual task, we won't have to use this upper part of the Excel file, so we're just going to focus down here for now, and here you can see these columns, that this is the link ID column, this is the link index, which we're not concerned about, this is the diameter index, which is the important thing we're going to change. So the diameters, the available diameter indices is numbers from 1 to 16. Number 1 means that we do nothing, and then number 2 till 16 are the 15 different diameter values that we saw in the handout. So there are 15 discrete values of diameters that we have to choose from in order to add in these duplicated parallel pipes. And the column with the pink background holds the diameter value in millimeters. So if we change one of these values, this is also going to change. In column A, we also have the pipe length, which is used in the equation in order to calculate the cost of the pipe. So I'm just going to change randomly some of these pipes. You see that also the diameter in millimeters has changed. Let's set another number, higher value, maybe here, just to see how diameter and the cost changes. So yeah, in this last column we have the cost, and then we also have the sum of the costs that we can see here. So this is what we actually need to see for now. Now let's do a random change here, maybe one of these pipes that are closer to the critical nodes, maybe 117. I'm going to set 5 here. Oops. So I set a 5 here, and this is the diameter in millimeters, and this is the cost of this change. So it's pipe 117. I think it's this one. Yes, it's 117, and I'm setting its diameter to 1828. Hit enter, and then let's run the simulation. So I ran the simulation, and as you can see, these numbers of pressure have changed considerably. If I'm not wrong, this was close to 30 meters, and this was less than 73 meters. So we see some improvement here, but still these values of pressures are way lower than the desired ones. That means we probably have to make other interventions as well, but we also are not sure that this is the best we can do for this section here. Maybe a smaller or a larger pipe in combination with other changes can make the difference and satisfy the minimum pressure at all nodes. So this is basically what we are going to do for this task. This is just a preview of what we're going to do during the live session, and we're going to experiment and discuss this in more detail then. For our third task, we're going to use the full potential of the Excel spreadsheet that we used before. So this is the semi-automatic process. So let's jump into our Excel file, and so now instead of using both EPANET and the Excel spreadsheet in different, let's say, windows, we can use this the full capabilities of this spreadsheet, which involves calling EPANET, so we can see also apart from calculating the costs, we can also see the results on the upper part of this table here. So down here we saw how we can calculate the cost based on the diameter index, but now we will also see in this part, in this section of the table, we're going to see the results changing. So I will just demonstrate this quickly here. I'm going to set some random values to these extra pipes, and here you can see that there are some calculated values already. So I'm going to initialize the model. I'm going to zoom out just for you to see part of the table that it's going to change. So I'm going to run the simulation. These values changed here. We see some improvements. For example, we see that we have no deficit for this node, this specific node, and I'm going to do some further random changes. So we see we have a big difference here, and the node IDs are number 18 and 19. So it's number 18 and 19 as we saw earlier in EPANET. So I'm going to change the values of these two pipes, 117 and 118. 117, let's set it to high value, maybe 13. 118, maybe set this to 10. And let's run the simulation. Now I ran the simulation. You see that most of the upper part of the table did not change, but we have no deficit for these nodes that we had a big deficit before. And you see that with some more improvements we can have no deficit at all. But let's see, here we have a total cost calculated, and this is $21 million. Here you can also see this penalty box, which is an extra, let's say, detail. So for each meter of deficit, let's say the water utility would have to pay a fine. So here we can see the sum of all this head deficit, and for each meter there is a penalty of $100 million, if I'm right. So this is something that should be considered as well in the total cost. So ideally we would like to find a solution where this is zero, meaning that we have no deficit at all in any node, and at the same time this should be the least possible, like the cost should be minimized. So you see there is a trade-off between cost and deficit and the penalty cost, etc. So this is let's say a multi-objective problem that we have to solve here. And again, in the live session there will be time for you to play around and see how each change affects the circulation of the network and how to try to optimize the solution. The fourth task of our tutorial is to solve this problem using the optimization tool of SolveXL. I'm not going to demonstrate this here, but we're going to see this together in the live session briefly towards the end. So for now, take some time to read through this handout. Don't worry if you missed something or you didn't understand something. We're going to discuss everything on the live session